Please join me in welcoming Dr. Simon Michaux, Senior Scientist in the Geological Survey of Finland. Simon is internationally recognised for his pioneering research into the material limits of the green energy transition. His work challenges conventional thinking, urging us to confront the realities of resource availability and sustainability. Simon's insights have informed policy and sparked debate worldwide. Tonight, he'll share his vision for an unconventional path forward, the purple transition. Over to you, Simon.
So I'm going to give you a rough description over the next hour or so of how I got here and what I'm doing. So to retread what I was saying before, back in 2005, I was working with the University of Queensland at the Julius Krutchnet Mineral Research Centre and Mineral Processing Engineering Research. And my job was to track the energy of energy consumption of grinding of rock. It's about half the cost of mining metal is grinding. And my job was to research ways like, can we do this more efficiently? And what I found was, in simple terms, that there were no shortcuts. Grade was going down, costs were going up. And there were a whole series of caveats. I also found a vulnerability for the mining industry at large to fossil fuels energy. That is, at the time, truck and shovel fleets were running on diesel, and everything else was electric, but that electricity was coming off a gas-fired power station most of the time. So oil and gas were the two energy feedstocks that were actually running most mining operations around the world at the time. I was posting the idea that if the peak oil thesis was correct, and one of the peak oil markers was in 2005, which it did plateau for a while in terms of production, if that was the case, then rates of mining would actually have to decline with the availability of fossil fuel energy. So there was a vulnerability there. And so what I presented this to the corporate Australia in the mining industry in a research thing, and let's just say it was a hostile audience. No one wanted to hear that kind of disruption to the market. Anyway, so I had this idea of energy and fossil fuels. I left Australia, the mining industry crashed, and I left Australia and I left mining to come to Belgium to learn industrial recycling and the circular economy. And what astounded me, I used to sit in the European Commission meetings and listen to all their visions for the future, and the masters of the universe were handing down the tablets of how things were going to be. And I heard the most spectacular bullshit. What these people were talking about for the future in terms of, like, coming from the Australian mining industry, all our concentrates was being sent to companies in China, smelters in China, where most of the time, not always, most of the time, the client. Now, in Europe, they don't mine things. Mining is considered unclean and dirty. What they do is they buy things off the market. So there was a complete disconnect in terms of there was the belief that we're rich, we've got the money, and while we've got the money, we can buy what we want, and that's all we need to do. Their plans for the future, when they were talking about the circular economy and the critical raw materials list, which I'll talk about later, which was the whole point of the Horizon H2020 project. What they were worried about was Chinese supply, the Chinese interest groups, was controlling the supply of certain raw materials which underpinned certain European businesses. They were very, very concerned. And as it turns out, they weren't concerned about the raw materials themselves. They were trying to support the longevity of European businesses. But this is where the CRM list came from. Now, there's a few furphies about it. What I was hearing about how they were going to phase out fossil fuels. And now I just come from Ausenco, which was, was supporting feasibility studies. What I was expecting was at least a scoping study level plan for macro scale reform, industrial reform, and it just didn't exist. And in fact, for entertainment, when you meet a politician, ask him about what new power stations are going in and what kind. If you really are phasing out fossil fuels, are you really phasing out coal and gas-fired power stations, and what are you replacing them with? And where? Who's going to own them? Who's going to operate them? And you'll find there are no answers. Anyway, so what I found was there was just there was a lot of what we call arm waving. There was a lack of numbers. There was a lack of details. There was a lack of reality. And a lot of what I heard in Europe was actually disconnected from reality, and they were making promises on behalf of both recycling and mining, which were never going to happen. And for about 4 or 5 years, I was sitting in these meetings, and it was just, it was like it was very disconcerting. Like reality was not being spoken about. Meanwhile, the existing system based on fossil fuels and mining, the way we always did it, ran along in the background. And so, well, that's mining, that's capitalism, that's just the way we do things. So the whole thing was a talk fest. I've since come to the conclusion that what we call the green transition was one big gigantic PR exercise to convince the voting public that there was actually a plan. Right, and I think what is in the process of happening is humanity has been walked to the edge of the pier, the veil lifts, and it says, sorry guys, the green transition's not really practical. Trevor did those calculations, he's not with us anymore. Not to worry, we're now going to have to make some hard decisions, here's our plan. And yeah, so what I was hearing was a disconnect between what was supposed to be sensible and what was a sensible plan going forward, and what they were saying. They had not done the basic homework needs of any of it. And I found this actually quite distressing, because in Australia, whole companies were going to the wall because they just didn't have the money. People were doing damn good work, and because the lack of money, whole companies were being retrenched. Whereas in Europe, the vast amount of money being thrown around on these projects that didn't really amount to much. And so for the last 7 or 8 years, I've been trying to work out a way of communicating what it was I was seeing in a way that couldn't be ignored. So what I've done is I've developed a bottom-up calculation. First, I looked at the fossil fuels industry. What does fossil fuels do for us now? We're a petroleum-driven society. There is a very strong correlation between GDP for a nation state and consumption of total liquids. Now, total liquids is anything you put in a internal combustion engine fuel tank. Is it gasoline? Is it diesel? Is it biofuels? Is it gasoline made from compressed natural gas? Essentially, it's a proxy for oil. So it's a very tight correlation, and there is no exceptions to high GDP, high oil consumption, low GDP, low oil consumption. Right, so we're a petroleum-driven society. We had a localized peak oil production in November 2018 of crude oil. Now, since then, we're getting more and more gasoline from biofuels and the gas industry in terms of compressed natural gas liquids. So what we call peak oil now has to evolve. And the gas industry is now propping up the oil industry. And it looks like that date is holding. That's now 6 years ago, even though consumption for total liquids is actually now going up and is now surpassing that date. But we've now seen peak oil. That's a problem, because our industry at a fundamental level is underpinned by crude oil at the moment still in the 2020s. Right, so I was to map all that out. What is our true dependency on oil, gas and coal? What does it do? All three fuels do different things. Oil supports transport. Gas supports heavy industry in the form of a gas pipeline to a power station. Gas also supports the plastics petrochemical industry. Coal supports heavy industry, but it also generates heat. And all heat that we actually sort of use in heavy manufacture, that's coal. All right. So then I actually looked at, all right, this is what we've done. So for the year 2018, I mapped out how big was the global system, how big was the European system, how big was the United States, and how big was China. And the rest of the world, summed together, gave the whole world. How big was the existing system industrially in terms of cars, trucks, trains, ships, aircraft? What I also noticed is when I was watching the work of others, they most always will talk about one small part of the system. They'll talk about passenger cars only. They'll talk about passenger cars in Europe only, but they'll talk about it like we will then, magic happens, grant us this miracle, and then we can go off and apply this solution. Not once did I hear someone actually get up and say, right, if we were to go down this path, we now need a certain amount of installed capacity of wind turbines. We need, say, 500-600 wind turbines of this size in this region to deliver power to this energy sector. None of that. And what was interesting was with each passing year, when you go back and reviewed all the presentations back to 2008, while they got shinier, nicer graphics, what they were saying didn't change. Now, the European H2020 project was given 99 billion, that's with a B, euros of funding. And in that time, they just put a whole lot of money on the floor. 400 universities and actors around Europe got employed. Everyone was great. Everyone funded their hobby horse, but there was no plan that came out of that. Apart from, we'll just use wind and solar. We'll just use electric vehicles and hydrogen fuel cells. And people had a tendency to reference other people's work. And so we saw the same thing again and again and again. But there was a lack of numbers, hard numbers, from a certain perspective, as in if you were to actually do this, what would it take? So I then worked out how many vehicles was there in the global transport fleet. And that basic question had not been answered. So if they can't answer that, how are they going to determine how big the battery industry is if everything's electric vehicle? And then I said, well, what physical actions did those vehicles take in a year, like one calendar year? Like what distance did they travel? No idea. Right, so if you don't know that, how do you know how much you've got to charge the batteries for? Like what extra electrical capacity is going to have to come off the grid? Then we come to, have you thought about how much you've got to expand the power grid? The answer is no. No, they had not. So there were very basic things that had not been done. And the more I looked, the more I found. So I decided to actually write a series of reports for the Geological Survey of Finland, Mineral Intelligence. I dreamed up this idea. My management, I explained it to them once the first couple of reports were actually written. Once I explained to them, they got it, and they said, all right, we'll let you do it. And I explained to them that with some back-of-the-envelope calculations, with the number of vehicles in the transport fleet, and I use cobalt as the example, if we had 1.4 billion vehicles in the globe, in the world, and each one needed a certain quantity of cobalt, that gave us a quantity of cobalt needed to replace the existing amount of fleet. I then showed that the amount of cobalt far exceeded reserves in the ground and resources that are known. And I pointed out to them that at some point, the captains of industry, in particular the big four car manufacturers of Europe, would turn to the geological surveys of Europe, Finland in particular, GTK in particular, because we oversee a batteries minerals portfolio. And they would ask us, why didn't you tell us about this very obvious problem? And once management understood that, all right, okay, we'll let you do it. Off you go. And so then I put together a plan, 6 publications that all fit together in a jigsaw puzzle to make a grander picture. And they were published in a reverse order, so people couldn't really understand what was happening. I've been sort of looking in researching information warfare and 5th generation warfare and all of that sort of stuff, and this was one of the ideas. Publish in a reverse order, so people don't understand that they see the pieces individually, but when it all fits together, then they go, okay. And I offended a multi-trillion-dollar industry. The finance sector behind wind turbines, solar panels, and batteries are most displeased I exist. And so I'm facing a lot of lobbying pressure from them. Right, so the next thing I sort of worked out, so we know how many vehicles there are. I then took each vehicle class, and we know what distance they travelled in a year, the year 2018. Once we have that, it says, well, if we take each vehicle class and we get a commercially available electric vehicle or a hydrogen fuel cell vehicle, if we were to substitute all vehicles for the selected vehicles, and in terms of the metrics, we can now estimate how much electrical power would be needed to charge all these vehicles, and what would their capability be. If each vehicle then had a battery in it, and there's some assumptions about what the battery market could be in 2050. For example, solid-state batteries will take 1/3, LFP batteries will take 75% of the heavy batteries. All of this came from the IEA prediction for the future. Right, so from that, we can now start to assemble how much, if everything's an electric vehicle battery or hydrogen fuel cell, how much hydrogen will we need? Okay, how do we make hydrogen? We're not allowed to use natural gas anymore, so we've got to use electrolysis. Okay. What will that cost? And so for each kilogram of hydrogen, it took, I think I estimated 50 kilowatt hours of electricity for 1 kilogram. Now, that was a very conservative estimate, but it meant that as innovations come along, the study stays valid for longer. And we're able to sum up the amount of electricity we needed to phase out fossil fuels. We need an extra 48,939 terawatt hours of electrical power generation across a year, in addition to what we already have in terms of non-fossil fuel systems. So that's transport. We also looked at what electrical power is generated with gas and coal and oil. Okay, so we've got to knock those out and deliver that power with non-fossil fuel systems. So now we have a sum of how much extra electrical power we need to deliver based on an energy mix proposed by the IEA for 2050. So, okay, they've given an energy split where wind and solar now take 70%, or I think 75% between the two of the whole energy mix. They become the primary energy source. If they did that, what was how many power stations we need? So then I worked out what was the actual power generation delivered in each for the year of 2018. What was the metrics for the average coal-fired power station, the average gas-fired power station, hydroelectricity, nuclear, wind, solar, biomass, geothermal? Okay, great. So we got some metrics now. So this is, if we need to deliver a certain amount of power, how many average-sized systems do we need according to this energy mix? And what I came up for there is we will now need about 800,000 average-sized power stations of non-fossil fuel systems. The existing fleet is 46,000. So it's more than 10 times. So what's happening there is if you take down a single coal-fired power station, how many solar panels do you need to put in its place? What I've done here is given a there's what manufacturers promise, but then there's actually what happens. Things like maintenance issues. By taking the average metrics, I was able to include availability. What was the availability in real time terms? What was the weather? What was the maintenance for all systems? Okay, so that was then applied to how many power stations. The elephant in the room, and this was quite a shock for me. I didn't expect it to come. Was the buffer required for wind and solar? Wind and solar are highly variable. They're dependent on the weather. And we've developed our technology over the last 2 centuries around the idea that we take fuel in a fossil fuel form and we burn it. And when we burn it, it's reliable feed. It's any weather, any location, and we control the power output from that burning to the point where our technology can depend upon stable electricity, the same voltages, the same current, and the same frequency. And it's a couple of weeks ago, there was a big blackout in Spain and Portugal. That happened through a massive change in frequency coming from solar power generation, and the whole system shut down, and they had to do what's called a black start. Right. Anyway, so the thinking behind wind and solar conventionally is we only need 5 to 7 hours buffer. And where that's come from is when they looked at supply and demand over about 40 years. And supply and demand goes along, and sometimes it separates, supply exceeds demand or demand exceeds supply. And all they worked out was you only need a couple of hours kept for about a week. to balance that out, and it was just a continuous cycle. That study, which was Net Zero America, they did not consider, for example, overnight. 5 to 7 hours won't get us through a single night. It certainly did not consider the difference between winter and summer. The sun in summer is stronger than the sun in winter. Now, I put together a series of case studies from around the world that looked at solar performance across the seasons, and they all said the same thing. And I did a study in Hawaii where the sun shines pretty well. In fact, this is the link that you've got, Andrew, the Hawaii report. In that is a calculation of if the whole system was solar and you had to deliver the same amount of power all the time to meet the metrics of the existing requirements of the Hawaiian system, we needed an installed capacity of 31 gigawatts of 18.7 gigawatts to deliver 31 gigawatt hours across the year. But based on meteorological solar radiance measurements in Hawaii, on the island of Oahu, we had performance of different solar panel types. There was solar panels mounted on houses, solar panels mounted on commercial buildings, parking lots, fixed mounts, and movable mounts. Each one had a performance metric, and that performance metric changed across the year. So we had a certain split across the systems, and then it worked out, well, if we were to actually sort of deliver the same amount of power, you have at the halfway, we could actually sort of collect power during summer, but we then have to store it. We would have to store 28.8 days of capacity to get through the winter to make sure the same power output was delivered. So we'd have to store it for 28.8 days, and it would have to be stored for about 112 days to get through winter. The problem is that all our existing thinking does not account for this massive amount of storage. They just haven't thought of it. And the technology doesn't really exist to store such a lot of power. Most of what power storage has done at the moment is what's called pumped hydro storage, where you've got a hydro dam or a hydro system on a river, and during the night and off-peak it pumps water into a reservoir at altitude, and during the day, during peak, it then runs the water down the hill and generates more electricity. Now, it's good for smoothing things out, the difference between the day and night cycle. And it's the cheapest way of storing power. It's got about an 80% round-trip efficiency. The problem is, with pumped hydro, is the sheer amount of power that we need to store and deliver will knock out about as much fresh water, about 48% of the existing draw of fresh water across the planet. We will need a lot more fresh water. We can't use seawater because most of where we need to do this is actually inland. In the areas that you can do seawater, you've also got other problems of actually sort of other logistic problems to actually sort of do this, and you've got the corrosion problems of working with seawater as well. So pumped hydro had its issues. Hydrogen as a storage also had its issues. To make 1 kilogram of hydrogen, you've got to spend about, by the time you have the power generation, compress it into a tank at 700 bars, and a few other transport things, we worked out you need about 57 kilowatt hours for a single kilogram of hydrogen. Now, when you put that through a PEM cell to get the energy back, you're getting about 20 kilowatt hours back. 57 in, 20 back. You've got about a 26% round-trip efficiency. And that's just a straight generation. Storing hydrogen's a problem. It tends to make everything brittle. It leaks. There's transport problems, there's storage problems. But just at the power generation level, 26%, that's a problem. So hydrogen's not going to work at scale. All of these technologies work at a small scale. The trouble starts is when you want to make them standalone and make them available for 8 billion people. So this is not a technology issue that I've come across. It's a logistical issue. Right. So what this work came out, all government groups I spoke to around the world believed that they were going to make power storage out of battery banks, like the battery banks system in Australia. I think, yep, this is great. How many battery banks do they think they need? and the number is thousands, tens of thousands of new systems, and the infrastructure is huge. And that's where wind and solar actually fall over. It's the need for power storage. Wind and solar. Then when you work out, well, how much metal do we need? So you sum up all the metal parts. So the laundry list of what we need. So this is in the slide deck. Okay, to phase out fossil fuels and maintain the same footprint that we were in 2018, 1.41 billion vehicles traveled 16 trillion kilometers. Right, so we need 48,439 terawatt hours of extra capacity to generate electricity to support that in a non-fossil fuel section. We now need a fleet of 800,000 power stations to make that happen. Included in that, and to be operational, 1.39 billion electric vehicles, 65 terawatt hours of batteries for those vehicles, 29 million hydrogen fuel cells, 38 billion PV solar panels, that's 450 watt, 1.3 million wind turbines of 6.6 megawatt installed capacity. The stationary power storage, which ranged anywhere from 25 terawatt hours out to 8,000 terawatt hours, depending on which buffer storage you believe. To me, the 28 days is the most sensible. Then we were going to build a series of new nuclear power, new hydropower, new geothermal, and new bio-waste systems. All right, we worked out, given that, what is the material content of each of those units? Sum it all together. So now we've got, in terms of aluminium, copper, zinc, magnesium, what have you, a number of how much metal we need to do this. So the next question was, well, how do we deliver this? So the first question was, well, at the moment we think in terms of mining. So can mining deliver? So looking at just copper, in 2019, which was the last year before COVID hit, and the supply disruptions from after COVID have put some really weird data artifacts in. So I use 2019 as the last sensible year of data most of the time. 24.2 million tons of copper was brought to market in 2019. Now, if we had the whole system and we just needed 6 hours buffer as conventional thinking believes, we only need 12 years of production. Now that's almost livable. Not really, but you can sort of squint at that. Yeah, okay, maybe we can do that. But if the real number is 28 days, now we need 6.1 billion tons of copper, which is 254 years of production at the current rate. More than 200 years. Now, the funny part is we want to get this done in 25 years. We have to get this 100% done by 2050. Right. The whole problem is the green transition is materially intensive. It's infrastructure intensive. It's vast. Much more so. Now, we've got the most complex industrial system the world has ever known, built in the last century on the most calorifically dense energy source the world has ever known. That's oil. And we want to knock that out and put in its place a fundamentally different energy system that operates differently. It's not as flexible. Right, and it's going. There's simply more parts to it, more materials to it, and this is the part that has not been discussed. So the whole green transition in its current form is not going to work. Now, since I've done this work, there's been multiple examples around the world that have demonstrated this. I believe in London, in the UK, they recently had another power blackout, and all the trains ground to a halt. There was the Spain-Portugal example. There is examples in Germany. Where they've actually sort of shut down their nuclear stations and their coal. But now things have failed. Now that the Russians have shut the gas off. Now they're wondering what the heck to do. So this work was very controversial to start with, but it's now becoming self-evident that the green transition, as discussed in its current form, simply is not going to work. So then the question is, can recycling help us? If the European Union is pushing the idea that recycling is the answer, we're going to get all of our raw materials from recycling. We don't need mining at all. Only dirty, unclean countries think about mining. We're superior. The number of times I've heard that outside Europe, it's, oh man. Right, so let's take copper. Now, if I was to take everything that's been mined between 1990 and 2023, that's 34 years. The last 34 years of data that was available. If things have, say, a 20-year life cycle, we mine it, we make something, for example, a car, use it, and then we'll throw it away. And so it's either been recycled and still in the system, or it's on a waste dump somewhere. 34 years should be well enough for that cycle. So if I was to go out and get all the copper that was mined in the 34 years, find those waste dumps, get that copper out, extract it, get 100% recovery. We've now got a stack of copper ingots. Will it be enough to manufacture the next green transition idea? The answer is no. That copper from 1990 to 2023 was 520.5 million tonnes. To phase out fossil fuels with a 28-day buffer, we need 6.1 billion. That's about 7 or 8 times that historical volume. 11 times. It's 11.8 times. So there's not enough material in the system for us to recycle. So now we come back to something that has not yet been mined can't be recycled. So this is a mining story, not a recycling one. So much of what the European Commission is thinking in terms of the future raw material source has been fatally flawed and misdiagnosed. They think they're going to phase out mining without checking out what they really mean by that. So they have lined themselves up for a lesson in manners of unprecedented nature, which is why their geopolitical adversary, China, is manoeuvring into place where they've more or less won the lay-down misere. Right, so recycling can't help us. All right, so what about mining? So the problem is mining is the grade's been decreasing. And normally I would be throwing graphs at you right now, but this is all in the slide stack that is available to you. Most of the high-quality copper grades of, they were like around 15%, were all mined out in the 1850s. Now we've got copper grades as low as 0.1%. The last feasibility study I was involved in had a cut-off grade of 0.1%. And we've been able to get away with that by raising costs and applying vast amounts of energy to do it. So we've got two inverted pyramids. We've got, in the beginning, our raw material reserves were really small but high quality, at the tip of the pyramid, and now that's come out to the base of the pyramid where we've got these massive, massive copper deposits that are really, really low grade. At the same time, we had this inverted pyramid for energy where 100 years ago, you had these massive, massive oil reserves like Gawa in Saudi Arabia, really big and really high quality. And now that's shrunk down to, well, now we've got Canadian tar sands where the energy is there, but we've got to work so much harder to get it. So these two trends, when they come together, are going to disrupt the whole plan. This will actually disrupt the whole idea of economics will sort us out. The costs will just be forced to keep up. We'll find a way. Those two trends, when they sort of come together, will have a rate step change that will force an entirely new situation, would have to be developed. And this is an engineering problem. You've got an engineering problem with specific metrics. Okay, so then there's discoveries. So people around me sort of think in terms of, mining's easy, someone else does that, it's not our problem. Right, here's the time it takes. Exploration time to discover deposits, so you've got a mineral resource, is between 5 and 20 years, when most of that time is tied up in getting permits for drilling. Now to take, so for every 1,000 deposits discovered that are mineral resources, only 1 or 2 become mines. Right, so the time taken to take a mineral resource and turn it into a mineral reserve with a feasibility study is about 7 or 8 years. Again, it's drilling and permitting. The time taken to take a feasibility study, report of mineral reserve, and turn it into a producing mine is 15 to 20 years. Again, permitting. And for every 10 producing mines, 2 or 3 will lose money and shut down due to market volatility. So we've got to, depending on what you're doing at, is mines and deposits tend to be in the pipeline for 50 years, 20 to 50 years before they're actually operational. And in terms of copper, the large deposits discovered decades ago, we're discovering comparatively small ones now that are lower grade and harder to work, and they also tend to be deeper, which means they're more expensive. So then we get to the point where, well, can we keep doing this? So between 2020 back to 4000 BC, 4,000 years, the human species mined 700 million tons of copper. According to economic demand, if we continue on the same trend, growth is good, we're going to do the same thing in the next 23 years. So there comes a point where, guys, there's a problem. Now, take that situation, which is now, and add 6.1 billion tons. That's 6.8 times the historical volume for the last 4,000 years. At a fundamental level, this is a crap plan. The whole thing's just not going to work. So we've got to, the cliff notes. If you've been asleep for the last half hour or so, and the cliff notes are as follows: mining production, existing mineral reserves, mineral resources, recycling, and resources under the sea that we know of, all summed together, are not nearly enough, not even close, to manufacture the first generation of renewable technologies to phase out fossil fuels, as we were in the year 2018, 7 years ago. Right? The whole thing's not going to work. Fundamentally new thinking. This is not about making a more efficient solar panel or a more efficient battery. We need a fundamental rethink of everything. Okay, so this is the phase of the work. Green transition is not going to work. When I did my 2001 report, I did a tour of duty through all energy systems. I found a whole series of unconventional systems where the technology and science were relatively mature, but for ideological reasons or one thing or other, we had rejected them. So what I'm now going to talk about now is, well, all right, smart guy, you've scared us, now you're going to fix it. When I was presenting to government, which is about a third of the time over the last couple of years, without exception, every single one of them had the following 3 responses. 1 was shock. They just weren't prepared. 2, even when they were given time to do so, or they were seeing it for a second and third time, they could not refute what I was presenting them because I was using their own data. 3, without exception, they asked me what they should do. Now, initially I found this a little demoralizing. I think, I'm just a guy, just a single guy, with a cheap computer and internet connection. Really? You and your super powerful government department with all your resources, and you're asking me? One, I sort of got past that, and so it turned out I was in a relatively unique position, and so I gave it a go. So, treating this as a problem to solve, what is it we are trying to do? So instead of actually sort of saying, we will now force the situation and just we'll replace it with a new kind of car or a new kind of power plant to keep the existing system, scrap the whole thing, start again. What do we want? We want electricity generation, transport. We want to manufacture things. We want reliable and consistently stable power generation in all weathers in all geographical regions. We want that power in a concentrated form. That is, we want to be able to send, say, 50 megawatts of installed capacity to a single site. So we can run a smelter or a mine site. We want a low materials footprint. That's where the green transition fell over. We want, for each of these units, to have a long working life. So instead of them having to replace them every 5-6 years or every 10-15 years, we want them to last 50 years. Okay. And when they do come offline, they're designed to be recycled. That last part there, we don't design things to be recycled. It doesn't occur to us. It's not part of our business model. Things are not designed to be recycled. That's why recycling rates are so poor. Right. Oh, and we want a minimal waste plume with a very low environmental impact. It's not just emissions, but it's everything that comes off this industrial system. We want it to be a very, very low waste plume. Now, that's the laundry list. There was a time when I thought this was, we're not going to do this. But I now believe I can deliver on all that. So what I call the purple transition is 5 unconventional technologies wrapped around a reinvented commodities sector. At the very heart of everything, we've got to manage our commodities and raw materials in a much more effective way. What I call the resource balanced economy. The circular economy is a nice idea, but it's thermodynamically imbalanced, and it should evolve into something else. Not that it's wrong, it just needs to evolve. Now that we're actually going to do it, how will we do it? Completely restructure everything. So we've got to take our raw materials, value them more highly, manage them differently, manage our waste plumes differently, where what's in our waste is actually useful. So what we call recycling should be extended to industrial waste, and mining and mineral processing technology will all merge into one big spectrum depending on application. And we need to be much, much smarter in a more systems context about how we manage all that. All right, that's at the very center of everything. That will also change in what we use money for and what money actually is. Wrapped around that are the following technologies. First is, to generate electricity, is generation for nuclear power. Take the existing nuclear system and evolve it to the next step. I'm talking about thorium-fueled molten salt reactors that are small and modular. I went out to a factory in Copenhagen Atomics, and I had a visit and walk around. They're making modular reactors the size of a 40-foot shipping container that'll be ready for commercial use in 2028. Now, that 40-foot shipping container unit will produce 40 megawatts of electricity or 100 megawatts of thermal heat. So now you've got the system that would actually sit in that room, or I don't know if it would, 40 foot, 12 meters. They're actually quite small. It arrives on a truck. They will load 50 years of fuel in at the initiation, at the start. Next to it, you've got another system about the same size of a steam turbine, and that's your electricity. What that means is we can now decentralize the whole system. Instead of having like one big giant power station in the middle of nowhere, and then have lots and lots of users and a massive grid in between, every system, every hospital, every smelter, every mine site, every factory can have its own power unit sitting in the car park or off to one side. Now, what thorium molten salt is it's a fundamentally different technology that's almost not nuclear. The way it works is as follows. They take thorium and make a salt out of it. Thorium fluoride, thorium chloride. One of the two. This is not radioactive. It's what's called fertile. The hazard sheet says don't get it wet, it'll dissolve. Like you don't need specialist training to handle the fuel. You can make the fuel relatively easily as well. Thorium is 4 times more abundant than uranium. And what's also different, because it's a liquid fuel system, 96% of the fuel is actually consumed in the reactor and used, whereas in terms of solid fuel, uranium, only 3 or 4% is consumed. So it's much, much, much more efficient. It is smaller and orders of magnitude more efficient. The salt goes into the reactor. In the reactor, we get like a plutonium plug or something like that, and just get it going, and we bombard part of that salt with neutrons. The thorium-232 isotope gets transmuted into uranium-233, and the neutron economy can start. Uranium-233 is radioactive and it's hot. It melts the salt. The salt liquefies. So now you've got a hot liquid and it's kept hot by the radioactivity of the uranium inside the reactor. It then circulates around that reactor in a heat exchange system, and that heat can be used to turn water into steam. The steam turns a turbine, and the turbine generates electricity. Now, 2 things. First of all, it's already liquid, so it can't melt down. If it gets too hot, that system will, through what's called Doppler broadening, cascade over the top of itself and collapse. If it gets too hot, it shuts down. You've also got a freeze plug where if it gets too hot, the fuel just drains out of the reactor into separate tanks, which can be managed separately. You've got multiple safety mechanisms that will prevent a Fukushima or Chernobyl-like event. They're much smaller, they're much safer. The fuel manufacturing footprint is orders of magnitude smaller than uranium solid fuel. The waste that comes out is orders of magnitude less than a solid fuel system, which has isotopes that are not as nasty. The fuel waste, some of it can be recycled into the nuclear medicine industry, or you just store it, put it in a steel box, and or actually what's interesting is if you take the whole reactor, take all the fuel out, store the fuel for 50 years, because all that fuel gets transmuted into some very exotic elements. 40% rhodium is the simulation. Rhodium's really valuable. Right, so you just sit it there and just store it, and then you process out the last of the radioactive material, and you've got a vast amount of really exotic elements. So that's right. So that's an opportunity. The complexity of these things is, in terms of construction, is about that of a 3-bedroom kit home. At the factory I saw, that's not a problem. They're going to make one of these a day from that one factory. Most of the parts are stainless steel and exotic nickel alloys. You've got some exotic components in it, but then it's on a much smaller scale. In terms of staff, you need someone to run the equivalent of an medical isotope lab in a hospital. That's about the level of complexity that's required to run these things. The company that runs this is, there's about 15 around the world. Copenhagen Atomics let me in the door and let me actually take some photos, which I now use in the presentation that you've now got. They are planning, get this, not only is this a useful solution, the funny part is it's going to be cheaper. How about that? So they're planning to, they won't let you buy the reactor. They don't want someone like me opening up the reactor to have a look. So they will lease the reactor, they'll own it, they'll operate it, they'll run it, and they'll take it away from the 5-year maintenance cycle that's needed. And it's all very easy. It arrives on a truck. They will sell you the electricity at 2 cents a kilowatt hour, where in South America, for example, powers, you can get it down to 13 cents a kilowatt hour. It's cheap. It's small, it's cheap. And the opportunity is we can generate heat at 560 degrees Celsius at 100 megawatts of thermal heat, or 40 megawatts of electricity from this one shipping container sized unit. So a town would have one of these, and that's their power source. You don't need the big transmission grid, and it's decentralized, which means if one grid has to shut down, it doesn't take everyone else with it. There's orders of magnitude less materials needed to run this. All right, so that's one technology, thorium. Then you've got, we still need transport. So we probably will have electric vehicles in some form, but the batteries aren't going to be lithium ion. We're going to make them out of something else. Sodium, fluoride, zinc, iron. There's lots of things we could do. We're fixated on lithium ion because, well, someone made a decision and now there's a lot of money invested in that. And now, a couple of years ago, I was working in a battery chemistry project called Bat Circle. And you couldn't actually have a conversation about alternative battery chemistries that are not lithium ion. They actually said, we will not fund you if you try and propose this. Now they're starting to talk about sodium batteries, now that they finally understand that lithium has a problem. But every battery that I've seen still has copper in it, still has graphite on the anode, still needs some nickel, some cobalt. And it's just a question of how much. So what will probably happen is we will have less cars on the road, but some will be electric vehicles, but we won't have lithium-ion chemistry batteries. Also, lithium batteries have this tendency to catch fire. That's a problem. Because once they do catch fire, it's very hard to put them out, and you know, all the fireys run out of swear words and try to actually deal with the situation. Right, so batteries of different chemistries. That's number two. Number 3, our long-range transport for things like maritime shipping, probably ammonia-fueled internal combustion engines. Hydrogen is all good and well. To get ammonia, you've got to make hydrogen first, then turn it into ammonia. Storing ammonia is less problematic than storage large quantities of hydrogen. The problem is ammonia is toxic at room temperature as a gas to all living things, so it needs to be stored at 300 bar pressure. Okay, but we know how to do that. The Toyota has actually developed an ammonia-fueled internal combustion engine that goes into a passenger car. My problem is the exhaust that comes out of this has all sorts of nitrous isotopes in it. They tell me there's a catalytic converter system that actually sorts this out. Never believe a corporation when they tell you stuff. But let's say that is correct. If you have a motor that's untuned, you will have unburnt ammonia fuel coming out the exhaust. And that's just the nature of internal combustion engines. So, and if that happens in like large cars in large cities, people are going to get hurt. I don't think we're going to see ammonia-fueled ICEs in large cities. But it does tell me that the technology is stable. Maersk is actually sort of putting massive maritime shipping engines together. And they've been running them, again in Copenhagen, all the way out to passenger cars. Okay, great. So, but we can sort of see like if we're out to sea in a ship, if there's a problem with exhausts, there's not many people around, it can be managed without injury. So it'll work for ships, and it'll probably work for say intercity trains like freight and what have you. This is why I think we're going to fall back on electric vehicles again and hydrogen fuel cells for vehicles in cities. But you've got to make the hydrogen, you've got to make the ammonia. Right. I do think biofuels will keep aviation going, but only biofuels of genetically engineered perennial grasses. Like if you use conventional soy and corn, forget it. There's just not enough biomass that'll make it viable. But some of the stuff we looked at in Hawaii, where we looked at a perennial grass that was 5 or 6 times more productive than conventional corn, that might actually bring... if the numbers are real of what I looked at, that could make the aviation transport industry viable once more to make jet fuel. Next one along is we need to replace coal. Now, coal is not just an energy source to generate electricity. We need to use it to make heat. Now, when we're doing a lot of smelting and a lot of industrial practices need up to, say, 1,500 to 2,000 degrees centigrade heat to operate. Now, that is going to be a problem, because if we're not allowed to use coal or gas anymore, options are limited. You can burn hydrogen, okay, but you've got to make the hydrogen, and the amount of hydrogen we're talking about is enormous, to the point where it's impractical. Then you've got the idea of an electric arc furnace, which, sort of works, but it puts a lot of strain on the electrical system, like how much extra electric power has got to come off the grid for that, and it doesn't work everywhere. And the third one was biofuels. Some biofuels could be used to generate that kind of heat. The problem is, if we're going to phase out fuel, like coal, which is like compressed biomass, and replace it with biomass that we grow, the planet's not going to be able to give that amount of biomass. So that's not going to work either. What I'm proposing is we replace coal with a metal fuel, iron powder. The powder that we use in the powder coating industry, like between 1 and 100 microns, really fine iron powder. It's harder to get going, but once going, it burns at around 2,000 degrees centigrade. We've got plenty of iron. Now, what's interesting, so we can generate heat. There's a pilot scale unit in the Netherlands that was, I think it's a 100 kilowatt system that it would sit in that room, from what I could see. They put it in a brewery in Bavaria. And so a system that will sit in that room can be generating 2,000 degrees centigrade heat. What's interesting is the iron fuel is not destroyed. Pure iron powder becomes oxidized, rust. If we strip the oxygen out of that, we can recycle the fuel. So we don't need more iron powder, we just need to strip the oxygen out. Now you can do that electrochemically. We're backed by a thorium molten salt reactor, okay. You could also do it in a syngas atmosphere or a hydrogen atmosphere. Here's where it gets interesting. This is the circular economy stuff. If we took human sewage and we put it into a pyrolysis plant, which is heating without oxygen, that sewage breaks down into a biochar which can be used for agricultural purposes, and a liquid that comes with it, but also about 35% biomass goes to gas, syngas, half carbon monoxide, half hydrogen. Both of those gases are useful to actually put into a process to strip the oxygen out of the iron oxide powder. With when you end up with water as the output, so that iron powder could be recycled. So now there's a link between a waste product from a human settlement, sewage, which is a problem, and recycling of an industrial fuel for manufacture. So, and when I did it for Hawaii, the numbers do line up. We actually ran out of sewage, and so it has its place. But we're now back to being very careful and frugal with regard to what we do with our the choices we make for our industrialization. How many cars we have on the road, what they're for, what industrialization we do use, and so on. There's a few other innovations I've thrown in, things like 3D printing and waste transfer. We don't have time for that. The final piece of technology in the purple transition is a new kind of transportation. When you actually look at the energy balance of the equation before and after, phasing out fossil fuels, trucks are taking a disproportionate amount of energy. The assumption was all trucks are hydrogen fuel cells because for logistical, practical reasons, but you've got to make the hydrogen. They were taking a vast amount of energy compared to everything else. So instead of phasing out trucks, our society runs on trucks. We can't just phase them out. What we need to do is, can we deliver what trucks do without trucks? And so I proposed the idea of what's called the spine rail arterial system. When you actually look at truck routes and truck transports, it's non-linear. There's many trucks going down a route between, say, a distribution center and a port, where 80% of trucks will go down that route. So instead of replacing all trucks, we will replace some of them. And the thing I saw at a mine site was when they're moving ore from the mine out to the port on a underslung pod system. You've got like a series of metal frames and a gantry, and you've got something like the size of a shipping container going on an underslung system that would actually shoot out along the route. So instead of a truck transporting a shipping container, we could have the shipping container itself being moved on such a system. So the idea was to put have a two-way system so shipping containers can move along this route, and you have a monorail system sitting on top of that to move people. So people and cargo can move along the same route without interacting at all. And when I actually sort of looked into the maths, if you were to apply that, this could involve a 25% reduction in the amount of electricity required to run the transport fleet if you had half the trucks replaced with such a system. That's the spine rail arterial. It might sound a little odd with that description. It's all in the report, the Hawaii report, and the notes to navigate that.
So I think we've got a room probably full of questions. You ready to take some questions?
Yeah, okay. Well, that's more or less it. Hit me.
Thank you very much, Simon. That's absolutely a brilliant presentation. Some years ago, I carried out quite a substantial amount of research into electrical power generation in the United Kingdom, basically on the idea or the assumptions that people had with regard to hydrogen. And all the things you mentioned about hydrogen embrittlement, transportation of hydrogen, hydrogen leaking, and then the major issue, of course, which is not often talked about, is the calorific value of hydrogen being so much lower than a hydrocarbon. So where we could get away with a 2-inch pipe, we're up to an 8-inch pipe. And this was particularly applied to gas turbine technology, with the idea you could run gas turbines on there. But what the most startling thing for me was when I started to look into this, and people had talked about green energy, and my wife's always been very good at that, and it really winds me up, because what's quite clear about this in the United Kingdom, and it's just not talked about, is that at the present time, you have to run combined cycle gas turbine plants for at least 24/7, and 45% of the electrical load is provided by combined cycle gas turbine plants. So everything you said there really stacks up. And when people talk about here about, there's a lot of talk about net zero. And again, that's something that winds me up. And what I talk to people about when they talk to me about net zero is say, how can you possibly make a statement like that when we've got a figure now of how many kilograms of CO2 per kilowatt hour we're generating. So all of that makes incredible sense. Thank you very much. Brilliant presentation.
You're welcome, and there's more if you want it. What I mentioned too is the hydrogen economy is viable if we change how we make the hydrogen. So instead of actually using electrolysis, which puts a burden on the power grid, if we use the sulfur iodine system, which requires heat to do it, and the reason that failed, it was rejected, it needed a standalone heat source. Hang on, burning iron powder and a thorium reactor are both heat sources. And a combination of the two might be able to give us the heat we need. What that means is you can make hydrogen in a decentralized fashion. So instead of actually having a central point that makes a lot of hydrogen you've got to then store for a long time and transport it, you could have a localized power, like a servo station, like we've got for diesel at the moment, that could actually then generate hydrogen in a local form, and you could use it as you go. You don't store it, you use it. And it only works if it's decentralized.
At the moment, in the United Kingdom, there is no green hydrogen. All we have is grey hydrogen. And what most people don't realise, of course, when they're running hydrogen-powered fuel cell buses, is the level of CO2 required in the emissions of making that hydrogen, in many instances, is actually higher than running an ordinary IC engine. So there's an awful lot talked about out there about achieving net zero, and I just cannot see it in its current form. So thank you very much. I really enjoyed your talk.
So the best power generation source is students in a hamster wheel.
Thanks, mate.
Hi, it's Robert Vazilla, Chair of Engineers Australia UK chapter. Simon, thank you very much for your time this evening. It's been very informative, and I think there's lots of ideas that you've thrown out to this audience. It seems that we're at the initial stages of a huge transition in the energy world, and I don't think the story's been written. And I think your input is really important to bring out ideas of alternative ways forward. I mean, particularly about the thorium, about the iron using, because there are specific high temperature heat source requirements. So thank you very much for your input. By way of a question, because we are Engineers Australia, although we are here in London right now in the UK, and yourself, you're in Europe, but bringing it sort of, let's say, back home to Australia, I think we're potentially sort of a two-edged sword where we're highly reliant on coal and gas as exports to pay the bills. And in Australia, we need to find a new form of export, of international income, but also to power ourselves, to power industry. And I think this is a great opportunity that you've brought out here today. So for a question, I'm trying to make a question rather than a statement. Do you see Australia as being particularly, we're a lucky country. So do you see greater opportunities in Australia compared to the international context?
Yes, but I did a study for the Australian Parliament. There was an inquiry into electric vehicles, and I banged out a report for them. The Australian, if the entire transport fleet was to go electric vehicles, just electric vehicles, how much would be involved with that? And they would have to expand their power grid by 33% just to charge those electric vehicles and run the same kilometres. That had not been considered. But that is all they would consider. It was either what we're doing now or the green transition. They couldn't conceive of an idea that there might be something else. And what I'm trying to get at here is we've got to get out of our own way. Much of what I presented to you before with regard to the purple transition was rejected as in, oh, that's crazy town. That won't work. That's the result of lobbying. In 1972, thorium molten salt was proven to work by the Oakland Ridge Nuclear Laboratory. They said, look, several decades of research, it works. We want permission to make a full-size system. The American military had it shut down so they could have a civilian uranium solid fuel system to camouflage the production of nuclear weapons. So it was ideology that killed thorium. The Chinese are now running thorium ever since 2022 commercially. So our geopolitical adversaries are out the gates and doing it. So when we're talking about people in Australia, decision makers, oh, that can't happen. It's now happening at the same time as their existing plans are crumbling. The Hawaii report, which you now have, was written for the Senate of Hawaii. If you were to phase out fossil fuels in the Hawaiian value chain, what are your options? And every single policy was looked at. Okay, it's 1,400 pages. If you're thinking in terms of systems and you've got to cover your ass, that's how you end up with these large reports. But if you go into it, especially in the appendices, how it all works. What the Hawaiians are actually starting to see now is their existing thinking is not going to work. In one of the appendices in that report is a game theory analysis of what happened on Easter Island. And the message to the senators of Hawaii is, if you make a mess of this, this is what will happen to you. And that, while it's a bit close to the bone, it did get their attention. And so now they're actually starting to consider the unorthodox, and that's the process. If we can get our policy leaders to consider the unorthodox, these are ideas, there are others. But if we can start thinking outside the box and look at, so can we look at other solutions? Then all of a sudden, places like Australia do have opportunities, lots of opportunities. And those opportunities, when you actually think in terms of a decentralized power grid that has a small materials footprint, the distances Australians have to cover all of a sudden are not a problem. You don't have a massive transport, you don't have a massive power generation grid that's very unstable. Simple answer, yes.
Simon, Andrew Gould here. I've got a question, and it's an AI question. Yesterday, Meta announced they're going to contract a company to build them a nuclear plant, and months ago, Microsoft did a deal with the 3 Mile Island plant to reopen that in 2027. So with the increased power demands from AI and generative AI from all these GPUs, where's the energy going to come from, and do you have a concern about it?
So there is a lot to be concerned about AI. I think their plans for their future are going to be hit with multiple black swans. They are going to force the issue. It's just not going to go the way they think. The amount of power that they want for the AI, no one's made a successful case to me about why this needs to happen. Why are they putting in such a vast amount of infrastructure for all these data centers? It sounds like ideology to me, not a business case. However, they're going to do it. The people who want to do that have finally done the math, and they realize that they're not going to be able to run these data centers off wind turbines and solar panels. So what they just said, instead of actually poo-pooing small modular reactors, they said, well, small modular reactors are the only way forward. And overnight, it became politically correct to talk about small modular reactors, next generation nuclear. Right, overnight. So while I think the whole AI debacle is going to be a problem, what they've done is blasted the door off its hinges. They haven't opened the door, they've blown it off its hinges. And now certain things are allowed to be discussed. In the conventional system, the power requirements of AI that we think is going to happen is simply not viable. It's just not going to happen. Right, unless they pull a rabbit out of the hat, for example, AIs that require less power. And I believe the Chinese DeepSeek innovation was in line with that. I think that debate is really going to force discussion out in the open, which has been kept undercover for a while. One of them is, we're not going to get the power to do this. We're not going to have the power to service our existing society. Our existing power grid is aging. The average power station is like 34 years old globally. It's something like that. The grid between the power stations is also aging. The way it's been designed, the way it's being built, requires constant maintenance, and which is often the case. People never do maintenance properly. And we've gotten away with it with positive thinking and chewing gum. And they think they're going to double or triple our electrical demands by electrifying everything once we get rid of fossil fuels. Ho, ho, ho. It ain't going to work. So it's going to be a big old mess, is the answer. That they're not going to get the power they're going to think they are. But in trying to get it, they might actually sort of force out some innovative solutions. As for AI, people ask me, like, how do we use AI? What should we do about that? We can have a discussion about that, because I've been asked by many students, like, what do we do? Do we use AI or not? The cat's out of the bag, but society is changing in ways that we don't understand yet. We've got to face AI in a way where we control it. It doesn't control us. How do we do that?
I'd very much like to thank you for your talk today, and it's been, as I said, most informative. We understand your time is valuable. You've got some brilliant ideas you've put out there, and once again, on behalf of Engineers Australia UK chapter, and we have some engineers from New Zealand in the audience as well. Thank you very much for your talk. Thanks for joining us.
Come and find me if you want me to explain things further. My work is public domain and available for everyone. If you want the Excel spreadsheets behind the work, I can give you those too.